All right, we are recording. Let's get it set up from the current slide. Okay. Now, what I was saying before some of you came in, I was apologizing for being a little late getting here because I tried again. I called yesterday afternoon to talk with the guy at Sanford because I only have office hours on Mondays and Wednesdays to speak of. And but I got so tied up with other things during the day, by the time I got around to calling him, I happened to look at the clock. It was after 5. I said, "Oh no, I'm going to miss him." And sure enough, it went to voicemail. So I told him, "Don't bother calling back today because I'm probably going to be in the office at all." And Friday, we were going to be out of town, so I was going to call him Monday again, or for him to call me between 4 and 6 on Monday. I mean, between 2 and 6 on Monday. Well, since my last class ended right at 11:50, I hustled down to the office, and I had a few minutes, so I thought, let me try calling him again, maybe catch him before he's gone to lunch or something. And I did get to talk with someone. She sounded like she's a student employee, as I think how she said it, working with him this summer. And she said he is completely booked for the rest of the month, okay? And then it has governor's program in the morning, whatever that is, and in the afternoon there's another program. She gave a name for it, but I don't remember what it was called. And that goes sometimes late to the afternoon. So basically, it didn't look like there's any time for the rest of this month. He's going to be out of town the week of the 4th of July. So, but she said, but we might still be able to work out something, because if he allows them to run it, they may be able to run the show for him during the week of the 4th of July, because he doesn't have anything planned then, and Kayla's here. So, I'm talking about the Sanford trip. Nothing's available between now and the end of the month, okay? But the week of the 4th of July, either that Tuesday or the Thursday, sandwiched with the 4th of July right around it, the 3rd or the 5th, we might be able to go if he sets them up and allows them to run it with him not being there. So that's a possibility. She actually sounded enthusiastic about the possibility, but she couldn't tell me whether he would give them permission to do that or not. So that might work out. After the 4th, it's not as much going on, but she couldn't say for sure. So she's going to run it by him and either send me an email later, or I will, if I haven't heard by Monday afternoon, I'm going to call again Monday afternoon. This time, hopefully, do it earlier. But it sounds like they're busy all afternoon, so I may not get it anyway. But I'll give it a shot. Okay. So, at least I know this. No field trip on Tuesday. Probably not Thursday, probably not for the rest of this month. Now, is that too far removed from when we're doing this stuff, or to do it the first week of July, or later? No? Okay. So I'll still try to schedule it. All right. Now, I think I caught everybody when they came in. Where we are now, we're right near the end of chapter 16, okay? Which would be the end of the astronomy section, but we can't do the planetarium until later. So we will, knock on wood, finish 16 today, probably fairly soon today. Because we haven't finished the chapter, I'm not going to test you today. That'll be Tuesday. So the test on chapter 16 will be Tuesday. So the last 2 hours a day, from 1:30 to 3:30, is when we'll schedule the lab, okay, on 16. Now, you won't be able to do it all, because part of it is you're going to do at home, okay? I'll explain all that later. But the bulk of it we'll do in class. Because it's not going to be the whole thing, we're probably going to finish, sorry about this, a little early today, sorry, get over it. Okay, yeah, I know. What's that? No, I know. Okay, forgive me. I knew not what I was doing. Okay, so, all right. Say again. Okay, well, y'all are resilient. I really admire you. Okay, now, so that's the rest of the day. Will be chapter 16, and then I'm pretty sure we'll start in 17 before 1:30. Okay, we'll stop wherever that ends off, and then we'll start on the lab on 16. And then on Tuesday, we'll continue in 17. I don't know if we'll finish 17 on Tuesday. Depends on how much we get covered today. But at least the last 30 minutes will be the test on 16. If we finish 17 sooner, we may have time to do the lab on 17. If not, it'll be next on Thursday. So we'll play it by ear. Any questions up to now? And remember, every test, okay, you get the formula and equation sheet. So keep that in mind. All right, I think we talked about most of this slide last time. Okay? Okay? Did we? Yeah. The moon's orbit is inclined 5 degrees from that of the Earth. So most of the time, the moon is not in the Earth's shadow, and neither would the moon be between us and the sun. So eclipses are fairly rare. Okay? It requires proper alignment of Earth, Moon, and Sun, so that if they're anywhere, if that 5 degrees is anywhere outside the shadow of the Earth or not in the way, not going to have an eclipse. Okay? But all those few times, the conical shadows have two parts, and that's where the next figure comes in. Oh, yeah, I showed this one already. And the one thing I said was missing here is the fact that the Earth also has a conical shadow. Of course, it's going to be with the sun out here, there's the shadow of the moon. And this is Chikoi, right? Huh? Guy, I'm sorry. As soon as I looked up again, I realized I said it wrong. All right. No one else has come in since I called it. Okay. The thing I said I wish they had shown was also that the Earth has this conical shadow. But it's a bigger shadow and it goes further into space. Okay? Now this is the only showing the dark part of the shadow. There's another part of the shadow that is not as dark. This is the dark part that lets no light come in, and similarly behind the Earth. And the only place where an eclipse can occur, a solar eclipse, if the moon happens to be at this point crossing the plane of the Earth's orbit. Okay? Happens to be there. It may have crossed it an hour earlier, never see an eclipse. 15 minutes before, you might not see an eclipse. Okay? It has to be almost right there for enough time for it to happen. The last eclipse, when a couple of hours that you could see something, wasn't it? Seemed like that was right last fall. So a couple of hours. So 3 hours before, 3 hours after, everything's over. You wouldn't have even known it could have had an eclipse like that. The only time you'll see a lunar eclipse is when the moon is back here, but also it has to be there right when Earth's shadow is there. Okay? And that's going to be fairly rare as well. But let's look at the two parts of it. This is just showing the dark part, which they say here is the umbra, the inner cone, complete shadow. And the Earth also has an inner cone, complete shadow, that goes back that way, much further than that because the Earth is much larger. Here's what we mean by those. This is showing the solar eclipse. Okay? When that moon happens to be right there when the Earth is there, then it will cast a shadow that hits the Earth. And that dark part of the shadow, that's that cone you saw, that may just barely touch the Earth. Okay? And that's all it ever will do, is just barely touch the Earth, and that would be an umbra. And that's the only time and the only place you'll see a total solar eclipse. Now, that may stay because the moon is moving, the earth is spinning. It may stay there for a while, but move across the surface of the earth. If you think about it, the last one, the one that was back in October, I don't know where it started, but I know it went across Tennessee. It went across, I think, Missouri maybe. It seems like it went into Oregon. There was a path across the U.S. that if you were along that path, you got to see it. We were a little bit south of the path. I think Nashville got to see a full solar eclipse. We had a partial eclipse. What does that mean? We were in the penumbra. Now here's what's happening. If you think about it, the moon. Now this is not to scale and nowhere close to scale. This shows the sun being smaller than the earth. It's nowhere close. Sun is huge. Earth is small. The moon is tiny. Okay? So, but the distances are nowhere close either. Okay? So they've done it so you sort of see this relatively speaking. Okay? So the sun, all of the sun's light going here in that umbra, none of the light gets through. It's all in shadow. But some of the sun's light casts a shadow here, but this part doesn't. So this is a partial shadow. That's a partial shadow. This is the umbra. Umbra means dark. So this is a penumbra, not as dark. Okay. And if you're in this band, you see a partial eclipse. Okay. Very, very narrow band will see a total eclipse, total solar eclipse. The bigger band, but not that big, will show a partial. That's exaggerated because they don't have the distance of light. Okay? But they've got it right for the umbra. Just barely touches. The inner cone, complete shadow. The outer cone is a partial shadow. Okay? Now the solar eclipses are where the tip of the umbra actually touches the earth. And that happened last October. There was a band so it was finite, not very much. I would say no more than 50 miles and probably less than that. If you were in that 25, 50 miles, something like that, you got to see a total eclipse. Total solar eclipse. I'm saying total eclipse. Okay. If you're outside of that, you got to see a partial solar eclipse. If you're outside of that, you didn't even notice it. Hear the news, you knew it was happening, but you wouldn't see anything that would let you know it was even happening. Okay? Now, the moon's orbit around the Earth is an ellipse, not a circle. Just like the Earth's orbit around the sun is slightly elliptical. A little bit closer in January, a little bit further in July. The moon's orbit is more elliptical than the Earth. So sometime that point of intersection that we saw here, if this is a time when the moon is further away from the Earth, then it may be that that tip of the umbra doesn't even touch the Earth. It comes close but doesn't quite get there if it's in the far part of the ellipse. Okay? And when that happens, you get what they call an annular eclipse. And the umbra doesn't quite reach the Earth. And actually, the last one, the pictures I saw looked like it could have been an annular eclipse. Because what you'll see is a shadow in the middle of the sun with a ring of fire around it. And it seems like that did happen because they were able to see features of solar flares and things like that that you usually don't get to see. So that's an annular eclipse. It almost looks like a ring. It's dark in the middle and you'll see brightness around the edges. Now, the lunar eclipse, turn this around, have the Earth here, the moon over here. The Earth makes a much bigger umbra and the moon's the same distance. So it's really a lot more frequently the moon will get in the Earth's shadow. It's still, everything has to be lined up. If it's here or there or somewhere else, you're not going to have a lunar eclipse. But if it is in the shadow, then lots of people will see a total lunar eclipse. And Many more will see a partial lunar eclipse if they're in the penumbra. They didn't show that for the other side, but that's where the moon is in the Earth's umbra. And the Earth has a bigger umbra, and the moon is smaller, so lots of things add to that, and you'll see it for longer. Now, let me point this out. What kind of moon is it when you see a solar eclipse? A new moon, because you're seeing only the dark side of the moon. This is the lighted side over here. We're on Earth, we don't see it. But when you see a lunar eclipse, what kind of moon is that? Full moon, absolutely, because you see it all except where it passes through the Earth's shadow. Okay. Whoa, okay. That's all they do for eclipses, except for the fact they have some dates in here. And obviously, they haven't updated this. The book was copyright 2017, and yet they talk about some lunar eclipses back in 2014. I'm glad they let us know that in time, okay? So, the total solar eclipse, and I said last October, it was last August. Last August. It was right after school started, now that I remember. In fact, it was like the first or second, what was that? Been the first week of class, I think it was. Either the first or second day the class met, I believe, because I don't even think I'd had a chance to tell them, you need to go out and see this. I think we may not have met for this class. The path went from Oregon to South Carolina, so I may have said it backwards. I was thinking it went from South Carolina to Oregon, but they say from Oregon to South Carolina. That went right through Nashville. Went right over Nashville, so they got to see it. We got it partial. The next one coming up, April 8th, 2024. They don't happen that frequently, okay? And that'll be from Texas to Maine. It depends on what part of Texas and what part of Maine, but that sounds an awful lot like it could go through. But we'll get a better shot at it then. Okay. Of course, by 2024, I'll be retired. If I'm still living, I'll be retired, okay? If I'm not living, I'll still be retired, okay? So, anyway. Total lunar eclipses, though, you see a lot more frequently, okay? 2015's over with. January 2018's over with. The next one coming up, January 2019, January 21st, 2019, that's next January, all over the U.S. The entire U.S. will get to see, like I said, that's a much bigger swath, okay? So the whole U.S., if it's not a cloudy night, okay, sometimes they're on cloudy nights, but you'll get to see the total lunar eclipse, okay? I don't know what time of night that'll be. It may be right smack in the middle of night, so you might not be able to see it even for that. 2 years later, there will be another one visible only at moonset. The next year, you'll have one visible at moonrise in the western, and all through the eastern you'll be able to see it. And in March of 2025. So sometimes there's as many as 3 years between. Most of the time they're either a few years, there'll be two in a single year. Most of the time it's 1 or 2 years apart, and there'll be 2 years apart between 2022 and 2025. Just not that frequently all those conditions are met, okay? Especially for the U.S. Somewhere else in the globe, yeah, they'll see them other times, but this will be for the U.S. All right, so that's one lunar event, sort of two lunar events that we pay a lot of attention to, and that happens to because of alignment of the Earth and the Sun and the Moon. Total solar eclipse, solar eclipses and lunar eclipses. There's another event that happens because of the alignment of the Earth and Sun and Moon. And these are our tides. Now, picture this. We're really a solid globe. Okay? Now, sure, 2/3 or so of that globe is covered with water, but only on the surface. Okay? Underneath the water is solid. Okay? The ocean bed is solid. Now, the ocean goes forever. Okay? Somewhere. So we're a big chunk of rock. Okay? With some water on most of the surface. Okay? Now, the sun is always pulling us toward the sun, and technically the moon is pulling us a little bit toward the moon. But the moon's much closer, so it has a greater impact, even though the sun is much bigger. Because we're so far away, it doesn't have as much impact, but it has some. Now, if you think about this, it probably pulls more. The water is flexible, it's fluid. So when the sun, let's say the moon. Did we do the moon today? Okay. So the moon's pulling us, and so the water will be pulled toward the moon, but then the solid part of the Earth will be pulled toward the moon, leaving water back there too. So you'll have a high tide here and a high tide there, basically about the same time. Okay? Whereas here, low tides, because minimum impact, 90 degrees from the moon. Okay. Now, if I happen to be in between the sun and the moon, increased. Because you're pulling water that way, you're pulling water that way, and smaller is here. So even stronger. Okay? So, result from different gravitational pulls on the front and back of the Earth, and the fact that water gets pulled, but the solid part gets pulled, so the water kind of, in a sense, bulges because it's pulled there. Three factors. I mentioned some of them. Number one, the Earth, Moon, Sun positions. Now, these are talking about high tides, but the spring tides are when the Earth is in between the Sun and the Moon. Those are the biggest, the largest tidal differences. Okay, the highest tides. The neap tides are when the Sun and Moon are at 90 degrees from each other. Okay, that way you're pulling this way, it's pulling this way, so it's the water has two different pulls and two different pulls there. So that's going to be your least amount when the Sun and Moon are at 90 degrees from each other. So that's one feature. The relative Earth, Moon, Sun positions. Moon position is more important, Sun though is secondary. But number two, remember I said the Moon moves around the Earth in an elliptical orbit, and it's a greater degree than this. So therefore it's going to have the greatest pull at the perigee, that's when it's closest, the less effect at the apogee, that's when it's farthest away. And there's about a 48,000 kilometer difference there, which if you remember, let's see if I can turn back and find it quickly. I doubt it. I don't do anything quickly. Okay. And I can't even remember for certain if it was this chapter or the last chapter that we mentioned it, because it seemed like it was. Seems like it's right in here. Maybe it didn't give it. I thought they did. don't see it. But the difference, I just don't see it. Okay. But what my feeling on it was, and I may be wrong on this, the difference of our distance, no, if I remember right, it was a few million miles. Seems like 2 or 3 million miles, and I said that's less than 2%, okay, out of 93 million miles. This difference here is a bigger proportion of our distance from the moon. Now that I know was in this chapter. I don't know if I can lay my eyes on that one or not. I don't see it here. I thought it was going to be pretty clear, but I don't see it. But this is a bigger relative difference between closest and farthest aphelion, perigee, and apogee and to the moon's orbit around us that our difference is around the sun. Ours is a bigger difference in miles or kilometers, but it's nowhere close to because it's 93 million between. This seems like to me it's around 400 and some odd thousand kilometers. But I can't say that for sure. I can't find it. So there's the second. Earth, Moon, Sun positions, and whether we're close to the moon's close to us, far from us, or somewhere in between. That determines how big the tides are. But the next thing is all local. It has nothing to do with the moon, where the moon is, where the sun is, or anything else. It's the topography of your bays. The size, shape, and depth of the water basin. Okay? If you're like the Gulf of Mexico, flat, long continental shelf, there's not a lot of change there, and this is highest, right? Okay. So therefore, very little range, generally about 1/3 of a meter, which is about a foot. Seems like it's a little further if you're on the beach, but again, the beach comes up so gradually, it takes a long time to cover a foot. Okay, so the difference there is a foot. Whereas on the Bay of Fundy, which I think was in Nova Scotia, 15 meters. That's a 5-story building, approximately. Because I'm about 2 meters tall, and there's another meter or so above me. So that would be a 3 meters per story. That would be a 5-story building. So can you imagine having your boat on that, or a dock on that bay? You have to have a pole that goes up and down 5-story building high. Otherwise, it's kind of crazy. So that's an extreme. And I believe it's Nova Scotia in Canada. That is. Okay? Most places are something in between the two, obviously. Okay? But when we were in Scotland, they have a lot of fjords, they call them, or they call that in Norway. What do they call them? Firths. They call them firths. Long, narrow entrances to the sea. I bet you their tides are much bigger than the Gulf of Mexico, but nowhere close to the Bay of Fundy. Okay. Now here is what I was describing earlier. The Earth is here with water on most of the surface. Okay? And when it's being pulled by the moon, that gives you a bulge in the ocean. The basic core of the Earth stays pretty much where it is, but it gets pulled too, leaving you a bulge in the backside as well. This is the tidal bulge left behind as the Earth is pulled away. This is the water being pulled toward the suspect there's a difference between these, though they don't say that. I would think this would be a little bit greater than that, but they don't specify, so I can't say it for sure. Okay, so that gives you high tides where this is occurring, low tides perpendicular to that, because water has to be pulled away from that. All right, does that make sense? Okay. Whoa. That was it for the chapter. Oh, one thing I may have said, but no, I don't think I said it. Myths, mistakes, and misunderstanding. Now, I think I've said before, sometimes these are pretty good to okay. Sometimes I think they're pretty weak. These are pretty good, okay, for the moon. This is on page 426. A common misunderstanding that the Earth's shadow creates the moon's monthly moon phases. No, that's the portion of the moon you're seeing that's lit by the sun. The Earth's shadow seldom crosses the moon. That's only during a lunar eclipse, and those are very, very rare and temporary. Okay, so that's one. Another is a phrase, and I wonder if you've heard this. Once in a blue moon. What in the world is a blue moon? Have you ever heard the phrase? Well, that only happens once in a blue moon. Well, here's what it is. It's not a reference to the color of the moon. Instead, it's a reference to an extra full moon that occurs in a season, which normally has 3 full moons. Okay? This doesn't happen very often, so that means it's a long period of time. And here's the deal, folks. Remember, I hate to do this because it takes so much time. That the average time interval between 2 consecutive phases is 29.5 days. Okay? Now, February will never have 2 full moons. Ever. Because it's only 28 days long. Okay? So it can't possibly have 2 phases. But guess what? All the rest of the months have a small, very tiny chance that there would be 2 full moons in that month. Okay? Actually, the way they say it, more than 3 in a season. Okay? But more than 2 in a month. And when that does occur, that second full moon that does occur that month, one would be very early in the month, the other would be very late in the month, 29.5 days away. But when that occurs, that's a blue moon. Okay? And Jacori's here. All right. So we're missing Cassidy and Lauren. By the way, I would be returning your second test to you, except one person did not get stayed to take it last time, so I have to wait till she does. I would be returning your second labs, but I've got several people who haven't turned in the second lab. Oh, getting more of them now. Okay. So I'll probably have, if this is everybody, I don't know if it is or not. If I have them all in, I'll get them back to you, hopefully by Tuesday. But if not, we'll wait on that too. Okay. So that's the blue moon. And then they say a popular myth has more accidents happening during a full moon phase. They say, however, studies have found no statistically significant relationship between the accident rate and moon phases. This myth is probably a result of people remembering the full moon phase, but not the other moon phases when other accidents have occurred. Okay? Now, all that being said, this will be mentioned in your lab today too. What's another name for a moon, or what's something that, for instance, what do we call a eclipse of the moon? A lunar eclipse. because Luna in, I don't know if it's Latin or somewhere, that's the word. Now, what word do we get from lunar? Another word. Referencing a person who's kind of off. Really off, huh? Lunatic, exactly. That comes from, okay. Now, the other thing that is attributed to the moon, and again, I don't know if there's anything, is behavior, okay? That, they talked about some werewolves or whatever howling at the moon, and it may be that it does upset animals and maybe people who are sensitive to that kind of thing. Now, we do know this. We had a neighbor who was really kind of nuts at one time. Not where we currently live, but a former residence we had. And you could almost map he was going to do something stupid around the full moon. I mean, we just started noticing they happened about the same time of the month, maybe not every month, but when he would do something, it seemed like near a full moon. Okay? And I've heard people from emergency room, EMTs and things like that, they say, oh no, it's a full moon, that they're expecting to have maybe accidents or maybe just weird things. I don't know. Maybe it's just that you remembered it when it was a full moon. Oh, yeah, that happened on full moon. And you didn't notice it when it was a new moon or a half moon or moon was up. Yes.
My sister was Lauren. They're saying because they say the first bad things happen.
Yeah.
Like most deaths,
yeah.
car accidents,
yeah.
people who are dead on the line.
Yeah.
It's just
So
hectic.
Yeah, they say here, research says there's no connection, but there seems to be. Otherwise, why would they have come up with the name lunatic? So I don't know. So anyway, just a thought, maybe not a good thought, but a thought. All right, let's see. I think we were at the last slide. So before we leave, just a couple of the questions that just has you doing useless has nothing to do with what we were talking about. How long does it take a reflected beam of light to travel from the Earth to the moon when the moon is 384,000 kilometers? So there it was, what we were talking about before. There's 384 kilometers on average to the moon, 48,000 difference between the apogee and the perigee. So you see that is a better than 10% of the difference. Whereas sun to Earth around the sun, 3 to 4% at most. This is more than 10%. So it's a bigger thing. And they let us know that that would be about there and back 2.56 seconds. And actually, during, I think it's your lifetime, I know during mine, they've actually been able to get a very good measure of the distance to the moon. Remember, the same face of the moon always faces the Earth, right? And when they sent up one of the Apollo missions that landed on the moon, one thing they did was put a big reflector on the face of the moon facing Earth. And it was a special kind of reflector like you have on street signs and bicycle lights, reflectors and things like this, that any light is going to get reflected and come back parallel, no matter where it's coming from. So they put this reflector, and every time, or for several times when they passed, they would shine a laser that was a very well-known wavelength and speed. They flashed that at the moon, and when they measured the time between the flash and the reflection, and they came up with an excellent measure of the distance from the moon. They had all sorts of other things before, but this time they had it nailed, okay? Now, something else, how far away is the moon if a reflected light beam takes 2.65 seconds away? Well, you can do the same calculation. That's how they did to measure how far it was from the moon. Okay, and they did it several different times and caught the apogee, the perigee, and that's how they know there's a difference of 48,000 kilometers approximately. One other thing that's mentioned here, or that they have here, people behind the science. They have at least one of these in every chapter. This time they focus on Carl Edward Sagan. Does anyone remember who Carl Sagan was? He died in 96. Were y'all even alive then? Some of you might be, I bet. But you may have been quite young. He had a television series called Nova. And they may still rebroadcast on I think it was on PBS. And he was a good scientist. He was a good astronomer. He's not one of the tops, probably. He hasn't done all that much that this shines him in pretty good light. But he was one of our best ever science communicators. I mean, he was good at science. I don't know if he came up with any bold, major things of his own, but he was a great communicator of science. So that's what he's best known for. My older brother, I mean, he followed them unbelievably closely. He still quotes what Carl Sagan said. Okay. But anyway, this gives a good blurb on him. He's a potential paper topic. However, this is not the source of your paper. It's where you can get the idea, but you'll have to go elsewhere to get your source. And there's several other things mentioned here. You can talk about any one of the projects he worked on. It says his first major research was planetary surface and atmosphere of Venus. Okay, so you can talk on that. I think someone chose that as a paper topic, didn't they? It seems like they did. But anyway, you might see other potential paper topics here. They mentioned two other people, Stanley Miller, Harold Urey. They did early work, so there's a lot there. These blurbs are well worth a read, not just for the information about the people, but other information as well. All right. I say it every chapter, I'll say it again. Nothing takes the place of reading the chapter. Okay? Please read them. Okay? Once you have read it, maybe a time or two or more, then the summary highlights the key features, but it doesn't cover it all. Okay? So don't think that's all you need to read. But this is a longer summary than many chapters have. It's the better part of a page, and then the key terms is one of the biggest lists of key terms I think I've seen in any of the chapters. Unfortunately, I list these in alphabetical order, but they do give the page number where those terms were first described or defined. Then applying the concepts is about average, 47 questions there. To me, those are the best things to study for your test. If you can do those and get the correct answers consistently, you are in a really good chance. These questions won't be on the test, but questions covering the same material, approached in a different way, could easily be on the test. Then questions for thought. I don't think any other chapter has as many as 30, and that's what this chapter does. They're usually in the upper teens, okay? So this has quite a few of those. For further analysis, it's about normal, 6, maybe a few more than normal. Now, the invitation to inquiry sounds a lot like part of your lab today, so we won't go into that. The parallel exercises these are the actual problems. They're like the examples in the book. Again, we're not going to focus on these too much, but if that's your bag and you like doing them, a really good thing. And if you have the big book, I know the answers to the Group A are in the back. I've not found them in the thin book. I don't know if y'all found them or not. Okay. Any questions on Chapter 16? What did I input last night? You have to have the second test for the problem. Yeah, it's a good I actually graded some of them Tuesday and other times, but I didn't get around to putting them in until last evening.
Okay, you were showing me what it was.
Yeah. Okay. All right. Now, any other questions? So the lab will be the last, we'll start the lab in about 30 minutes. So let's see what we can get done in chapter 17 today. Okay. Again, let's take a bigger view of things. We started with the universe. Can't get much bigger than that. Got down to our solar system. That was the universe was chapter 14. Solar system was chapter 15. Then the Earth-Moon system, 16. Now we're focusing on the Earth. Okay? And for the next 4 chapters, we're just going to be the Earth. Okay? Then the chapter after that is weather on the Earth. So again, the Earth. And the last chapter will then be the waters of the Earth. For these 4 chapters, basically is going to be our geology portion. Geology, plate tectonics, those kinds of things. So that's where we're starting in chapter 17. And I thought I clicked on this, but nothing happened. Let's see if I can make it happen this time. Okay, PowerPoint's taking a while. So, rest of the chapter focusing on planet Earth. We may mention the moon every now and then or other things like that, but now we're focusing on the Earth. And this first chapter, Rocks and Minerals, is, to me, the most geological part of this. And that is one beautiful mineral, okay? Your text has it slightly different form, but I believe it's the same mineral. These rose-colored rhodochrosite crystals, naturally occurring, nothing that man-made here. They form from manganese carbonate. Manganese is all that common. Carbonates are all over the place. Rhodochrosite is but one of about 2,500 minerals that are known to exist, making up the solid materials of the Earth's crust. Now, the interesting thing to me, especially the picture that's in the book, is the substrate on which it's formed. It's really a bright, beautiful green, which usually means either nickel or copper, I think, will produce that greenish color. Copper sulfate is kind of that color too. So here's this bright red crystals growing on a rock that's a fairly pretty shade of green. And you see a little bit of that on the edge of the crystals. Okay? Now, the title of the chapter is Rocks and Minerals. But how we're going to study the chapter, how they present it, is the reverse. We're going to do minerals first and then rocks. Okay? This is a mineral. Certainly it's part of a rock. It's stuck on something else, but this is a mineral. And there's about 2,500 minerals, they said, but there's how many kinds of rock? Almost unable to count. So, here's the core concept of this chapter. And this will be, you'll see forms of the same concept in a bunch of different chapters. Earth is a dynamic body. That means always changing. Always changing. That cycles the rocks and the minerals through ongoing changes. Always changing. Maybe the change is slow. Yeah, it is. You don't always notice it, but it is always changing. Remember the moon? It hasn't changed much in the last 3 billion years. Yeah, little things got hit by a few more meteorites and things like that, but it's pretty much stable. Okay? The Earth is fairly stable, but it is dynamic, always moving. Always moving, of course, but always changing too. Here is a rock, and we'll talk about this one later. You can tell it's made up of different kinds of minerals. There's a light-colored mineral, darker minerals, and things in between. This is one of the oldest rocks known to exist. it's gone through an awful lot of changes. It was a sedimentary rock. We're going to talk about this later. That was in flat sheets. And over time, it's gone through such changes that those sheets have been bent, compressed. I mean, all sorts. You can tell this had quite a history just looking at the shapes of it. We'll get to that later in the chapter. So let's start with 17.1, which is Earth Solid Materials. Okay? Or solid earth materials. Now, the solids in the earth, you know that most of the surface is covered by water. But underneath the water is solid. Okay? And all the land we live on is solid. These solid materials are a non-uniform distribution of matter. Here's just a really dumb example. If I were to go out and dig in some fairly virgin or clean new soil here, not going to be too long before I hit red clay, probably, right? I know over in Georgia that's the case. Probably here too. But if I were to go up to Winston County, which we're going this weekend, you're going to hit sandy stuff most of the time. You go over down to the Black Belt, you're going to dig for a long way and you get just really thick black material. Yeah, we're non-uniform. Some places have one type of mineral, some have another. What do we call Red Mountain? Why do we call it Red Mountain? Iron ore right near the surface. That's where they did the early mining, right? And in these areas as well. Tannehill, didn't they used to have a mine out there? Or some sort of thing out there. So yeah, that doesn't happen often. Over in Georgia, I don't know of a single place that has iron ore in mineable quantities. Birmingham does. So non-uniform distribution. That's a short distance between. Now, not only is it non-uniform distribution on the surface, as you go down, it's really non-uniform distribution. There are very distinct differences. Let's talk about the nature of these as you go down. Let's start at the very center. The core, I hate they say it this way because later they're going to almost contradict it. They say is molten, which means melted. Okay? So later we're going to learn you have an inner core and an outer core. The outer core is liquid. The inner core is solid again. Just because of all the pressure pushing in on it, it goes back to being a solid. So this says the molten core, and if you were to dig down, that's what you'd hit. You never hit the thing. Of course, you don't dig that far in. It contains mostly very heavy elements. The predominant ones are iron and nickel. Mostly iron, but then nickel. Okay? We don't have that much nickel near the surface. We have some places where the iron has made its way to the surface. There's one place that has probably a lot of iron these days near the surface. The big island of Hawaii. Why? Kilauea volcano is erupting, and most of that is pretty high iron content. Okay? So, because it's coming from way deep, that molten core, or maybe not at the core, but close to it. Now, so molten core. Then we have, and they're skipping several things here, then we have a very, very thin surface crust, mostly with lighter elements. Okay? So we're going to look at these two breakouts. There's a whole another layer in between these two. We'll talk about that a little bit later. 8 elements, only 8 elements make up almost all of the crust. Almost all of the crust. Okay? Now, the rocks and minerals make up the solid crust materials. I think they're going to talk about those 8 elements. Here we got in the Earth's crust. Now wait a minute. We're talking about solid material, and you say oxygen. Is oxygen a solid material? Not pure oxygen. No, it's a gas. They're not talking about oxygen in the air. But remember that crystal? That one? Rhodochrosite? It's a manganese carbonate. Okay, what is that? Manganese, there's probably one manganese atom in that. There's probably one carbon atom in that, and there are 3 oxygen atoms in that. So most of that is made of oxygen. I mean, it's hard to believe, but it is. Carbonate is CO3, manganese is Mn, and 3 carbons probably outweigh, but 3 oxygens way outweigh the carbon, and probably the manganese too. Let's just find it and check to make sure. Manganese is 55, basically, is the atomic weight, and oxygen is 16, so not quite. It's heavier in manganese than it is oxygen, but not by much. Oxygen would be 48 grams of oxygen for every 55 grams of manganese, and the carbon is a small 12 grams. Okay, so still, okay, I was not quite right on that, but almost half of that is made up of oxygen. Okay, so yeah, like I said, and you get other things like calcium carbonate, and most of what underlies Alabama, at least in this portion of Alabama, is limestone, and limestone is calcium carbonate. Calcium is much lighter than manganese, and carbon's still carbon, and the O3, 3 oxygens over, yeah. So most of what's underneath us, way more oxygen than anything else. It's oxygen combined chemically to form a solid, not gaseous oxygen. So even though that seems bizarre, it's true. And look at that. Almost half of the solid material of the Earth is composed of oxygen. Okay, not oxygen gas, but solid oxygen in crystal form. More than a quarter is silicon. Okay? In fact, you go out there and pick up anything in the ground. If you feel any grittiness to it, there's a real good chance you have sand particles. Okay? Sand particles are silicon dioxide. 1 silicon for every 2 oxygen. Look at that ratio. Almost 1 to 2 right there. Now, silicon is heavier than oxygen, but that's composing most of the surface of the Earth. Your silicates, actually silicates, are 1 silicon to 4 oxygens, but some of the oxygens are shared. After that, number 3 is aluminum, which is 8.1%, which is not even 10%, but significant. Okay? Now, is that aluminum you would mine? Most of the time, no. Again, that's going to be compounds of aluminum that aren't particularly helpful for mining. Well, here's why. I mentioned clay. Clay is always an aluminum layer. Yeah, aluminate and silicates in layers. Okay? Most of the clay around here is kaolinite, which is 1:1. So for every aluminate, you have aluminum in there. Silicate, you have silicon in there. Anytime you see H or I, that means there's oxygen in there, big time. So the clays, silicon, oxygen, and aluminum. Okay. After that is iron. Most of that iron is not mineable. Okay, though here in this area there was, and still is some that probably be iron mined, but generally not. In fact, what color did I mention the clay would be? Generally, not always. Red. Red. Where does it get the red color? Not from rhodochrosite, by the way. Iron. Iron ore. Iron oxide, which is another name for rust. Isn't rust sort of a reddish color? That's why the clays are red, because of the iron. So that's mostly where the iron is. Not mineable, because it's just small pieces of covering lots of area. After that is calcium, mostly in your carbonates. Rhodochrosite is magnesium carbonate. Rhodamine, by the way, means red. That's where they got that name. Limestone is calcium carbonate. Dolomite is calcium magnesium carbonate. So lots of calcium. Your Phosphates are usually calcium phosphates. There's calcium in several things. Okay? Now, we're talking about solid earth materials, but I'm going to mention a couple of others. The cell walls that make trees stand up, and plant material that has a rigid cell wall, it has calcium in it. And guess what else does? Our bones, our teeth. The hard stuff is quite often calcium. So where did that come from? It came from minerals in the earth. Okay? So that's only 3.8%. Sodium, again in minerals. What is one mineral that contains sodium? This will be in the ocean too. But we're talking about solid earth. You may have used it on your lunch today. Salt, sodium chloride. That's a mineral. Okay? Shortly after sodium is potassium. They're almost equal. And any of you use sea salt rather than normal white salt? It's healthier because it contains potassium, not just sodium chloride, potassium chloride. There's many others that contain potassium. We'll talk about some of the minerals. Micas, they high in potassium. Magnesium, that follows along with calcium. It's a little bit less. I mentioned magnesium carbonate. Calcium magnesium carbonate is dolomite. We have a town named that, right? Probably because of the dolomitic limestone. I assume they must have mined it there and had some of that. Magnesium sulfate is gypsum. I don't know if you've run into that before. Sometimes called land plaster. My grandmother used to soak her feet because she had gout in Epsom salts. Sodium, magnesium sulfate. Okay? And then everything else, 1.4%. Yeah. These 8, 1, 2, 3, 4, 5, 6, 7, 8, mostly these two make up 98.6% of the Earth's crust. What you need the others for, okay? Notice there's not much gold or silver or platinum in there. That's what makes them rare and very valuable. And in fact, don't combine much of those things. But if you talk about the whole Earth, that includes that molten core, and thinking this thin crust, that's awfully thin. Most of the Earth is made up of other stuff, and the biggest gain here is in iron. It goes from 5% of the surface to a third of the entire Earth is made up of iron. Most of it not mineable. Way, 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 way deep. Oxygen is reduced because most of that occurs on the surface, but still it's number 2. Silicon drops to number 3. Magnesium way picks up from 2.1 to 13.9. And nickel wasn't even mentioned up here, that was in others. Now it's coming in at 2.0%. Calcium dropped from 3.6 to 1.8, about half. Aluminum dropped from 8.1 to 1.5. Sodium dropped from 2.8 to 0.2. All the others, which would include some of these, but mostly others, still less than 2%. Okay? So, iron for the whole Earth, oxygen for the crust. Oxygen's still pretty big in the whole Earth just because there's so much on the crust. That's not gaseous oxygen. And it's not the oxygen in water, H2O. A lot of oxygen there too, but that's not counting that. This is only solids. Okay, so we've been talking about, and I said we're going to first do minerals. Let's talk about what a mineral is. This is 17.2. Here's the earth science definition, and it has at least 4 major parts on it, mostly separated by commas or conjunctions. A naturally occurring, that's one part. Inorganic, that's the second part. Solid is really a part of it too. Solid. Element or compound, okay, with a crystalline structure, that goes with being solid somewhat, So those are the major parts. Naturally occurring, inorganic, solid, crystalline structure, and it can be either element or compound. Okay? Now, going from the negative, cannot be synthetic, must be naturally occurring. Okay? So therefore, is that glass a mineral? No. We took a mineral, silicon dioxide, sand, and we melted it and did all sorts of stuff with it and got it into glass. So the glass itself is not a mineral, but it came from a mineral. Okay? Not directly produced by a living organism. That's what we mean inorganic. Organic, so is your bone or your tooth, is that a mineral? No, it's made up of, that came from living things. To be a mineral is inorganic, naturally occurring inorganic. Now, calcium carbonate, limestone, was a collection of very, very, very old stuff that used to be living material. So that is counted a mineral because the living material has decomposed, changed back to some other form. Because some limestone, you can actually find shells in them. The shell would not be a mineral, but the rest of it would be a mineral. Okay? So it's not directly produced by a living organism. Okay? That would beg the question of coal. Coal was one time peat, you know. Has it been long enough since it was a living organism that coal does count as a mineral? I think it usually does. Okay? I don't know that for sure, but it's not directly produced by a living organism. So your tooth would not be. I produce that myself. Okay? Must have a regular repeating pattern. That's what makes solid with a crystalline structure. That's the second reason glass would not be a mineral. You might say, well, I've seen glass crystals. Well, not really. If you break glass, you notice the breaks are never uniform. Some are curvy, some are sharp, some have to be a crystalline structure must have a repeating pattern. The example they give here is halite, which we've already used, sodium chloride, table salt. Now, the mineral halite, you probably wouldn't use for table salt, okay? It has other stuff mixed in it, probably. So they process halite, purify it, and that's what you use for table salt. Now, any of you make ice cream in the summertime? Ever heard of that happening? What do they usually put on the ice? Yeah, and they usually say rock salt. And when it's over at the end, it's little grainy, blackish looking residue with it. Salt is, gone away. That would be halite. The original rock salt is probably halite. Now, this is a decent illustration of what they mean there. This is the yellow is your sodium ion, and the blue is the chloride ion. Now, there's one error on this slide, and I hope you'll see it at some point. The structure is always these little cubes, and the opposite positions of these things are never does a chloride connect to a sodium, or a sodium to a chlorine. Never does a sodium connect to a sodium or a chlorine to a chlorine. Always the sodiums only connect to chlorine and the chlorine connect to sodium. So this sodium is connected to that chlorine, this chlorine, and that chlorine, only connected to chlorine. The chlorines are only connected to that sodium, that sodium, that sodium, that sodium, somewhere, another. Never to another chlorine. Okay? So, and that whole structure repeats and repeats, and these individual cubes connect to the other cube, and connect to the next cube, and stuff like that. That's a repeating structural unit. So halite is a cubic structure. Now, if you get some table salt at home, sprinkle it on something, probably something dark background, get you a really good magnifying glass and look at it. You'll see that just about every one of those little salt crystals is a tiny little cube. Some of them may not be perfect because they've been ground or something, but you'll see that cubic structure that repeats itself. Has anyone found the error yet?
Yeah.
Where?
You see where your arrow pointing right there?
Right. Well, not there, but yeah, here.
On down, yeah.
Yeah. This chlorine says it's connected to that. That should be gold. That should not be blue. So that should be a chlorine back there. That should be a sodium back there. Because sodium's on that. Yeah. They made a mistake there. Whoever did the graphics, shame. Okay. You missed it. Okay. And that's an example of your structure. Now, there are several different types of crystal structures. Okay? They name a few. Now, they can be made up of one element only, and they give an example here, or multiples. Okay? Diamond is pure carbon. Pure carbon. No other element in it. Carbon only. Now, what do we usually think of as carbon? Coal is almost pure carbon. It has some other things in it too. Probably purer than that would be soot. That stuff in your chimney, it's real black, and if you got it on your hands, it's real slippery. That actually is a mineral called graphite. Pure carbon. Okay? But it's slick. How about diamond? It's the hardest substance known, naturally occurring substance known to man. So, and graphite sometimes is used as a lubricant because it's so slick. Whereas diamond is your most abrasive substance you got. If we had some previous owner had poured a slab in our backyard that went more than the length of our house. This is back from our house. More than the length of our house and several feet deep. And there were pecan trees and other trees surrounded by this. And I looked at that and said, why? Why is there a slab back here with trees, surrounding trees and stuff? And the realtor said, I don't know. I asked the question, and one of the neighbors said he thought it was because they wanted, when the kids played in the backyard on swing set, so they wouldn't get dirty. I thought, oh yeah, much better to fall on concrete and not get your clothes dirty. That much preferred. Maybe rip the clothes up, break a bone, but at least they wouldn't get dirty. So I don't know if that's the reason or not. We had it, except for one portion of it. So I wanted it cut up. And we wanted to build a little shed on one end because the shed at the end of our garage was literally falling apart. So I had them cut off, and they came with a blade to cut through the concrete, which had rebar in it. So guess what blade they had to use? Diamond tip blade. No other blade would have come close to digging through concrete, cutting through concrete. And it cut, it cut smooth, straight, very well. Okay, they lubricated it, I think, with water, but yeah, diamond is the hardest stuff out there, and it's pure carbon. Graphite is another mineral that's pure carbon, but it's used as a lubricant. It's not abrasive at all. The difference, diamond is a three-dimensional crystal structure, very, very strong bonds, the strongest I know of, whereas graphite is a two-dimensional structure, crystal structure, and those molecules slide past each other so easily because it's sheets. So, two examples there. Quartz, on the other hand, is silicon and oxygen. Those sands, sand grains, quartzite. That's silicon and oxygen. So this is an element that's a compound. Okay, so it can be either one. Now, the classification for these crystal structures, don't get bent out of shape when you see these. And here, I'm not going to test you on these, but just so you'll be familiar with it, you've heard the term. The first of these is called isometric. When you see that prefix iso, that means same. An isobar is a weather map, and the curves that go around the high pressure, low pressure, Those are equal barometric pressure. Same barometric pressure here, here, here. You know, if you have a topographic map that shows isoclines, same elevation all around here. The ditch down here, you'd have same elevation here, 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 or a cliff. You know, so iso means same measure. So the one type is isometric. Okay. This is, remember that sodium chloride halide crystal? That was a cube. Those sides, the lengths of the sides are all the same. Isometric. There's an octahedron. Equal sides. Every one of these sides is the same dimension, same length. Okay? Here's a tetrahedron. Okay? And that each side, there are actually 4 sides to that. Sides, 1, 2, 3, 4. Okay, that's a tetrahedron. Octahedron means 8 sides. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then this is a dodecahedron, which is a 12-sided, I think. 1, 2, 3, 4, 5, 6, 7. I think it's 12. Hard to count. But all the sides are the same. Okay. Now, quartz forms the halide, the salt crystals are cubes. Quartz are basically tetrahedral structures. Your aluminum silicates are octahedral systems. I don't know what the decahedrons or whatever. So those are your isometric. Okay? Your hexagonal, that means 6 sides. Okay? This prism is hexagonal. These 6 sides are all the same. The top and bottom are not. Okay? The dimensions are not. These lengths are different from this. This is a rhombohedron, which basically it has 6 sides. 1, 2, 3, 4, 5, 6. Well, so does the cube. The difference here, these sides are not the same length. Okay? That's hexagonal, 6-sided. Okay? Tetragonal is 4-sided. Now that's 4-sided, but these are isometric. Here's a tetragonal that is 4-sided, but they're not equal length sides. Okay? And this is a prism. And you'll see quartz has some of this nature to it too. You'll see pictures of the mineral quartz like that. I said it was the silicon dioxide is a tetragonal structure. The quartz is a mineral that is more than prismatic structure. Okay? Orthorhombic. Okay, now the rhombic, we saw the rhombohedron, that's not equal, usually not equal angles. Okay? So orthorhombic is it's a 6-sided, but it's not counted as a hexagonal. It's just a prism, and my guess is the angles are not equal. Those look like they could be. These probably are squished. For instance, a square, you know what that is. 4-sided, all the same, and all right angles. So all angles are the same. If you were to sit on a square and it goes like this, that forms a rhombus. That means it's still 4 equal sides, but now the angles are equal. 2 are small and 2 are big. So that's rhombus. So my guess, that's what orthorhombic means. Now, rhombohedron, I'm not too sure why they use the same figures. Monoclinic is this one here. I have no idea why they call that a monoclinic. Mono usually means 1. I don't see any oneness in that. And then triclinic usually means 3. I don't see anything to do with 3 there. These are both prisms. So you don't need to know these, but in case you ever run into the word, oh, I've heard that before. Tetrahedron, 4 sides, equal sides, octahedron, 8 sides, equal sides. You know, cube is 6 sides, equal, equal angle to the decahedron. Every dimension is 12 dimensions there, or 12 sides there. All equal. Okay. Don't sweat the big words, okay? And here's some pictures of this. This is a picture of that table saw that we touched at. It's structure unit for table salt are these little cubes. You see they're not all perfect cubes, got another glitch in it, you know, but they were all cubes to begin with. Now this was your hexagonal prisms. You see there's that top. Oh, what a beautiful crystal quartz. And we'll see some occurring in rocks. I have picked up samples of it someplace or another. So you see these crystals you show up. Those are the minerals in the rock. We haven't talked about the rocks yet. So, we will pick up next time with silicates versus non-silicates. Okay? Because it is time, right? So we'll pick up on page 439 with the silicates. Okay. Now, y'all need to take a break before we get started on this? It's a good break time if we're going to have one. You do want one? Sorry, let's pause. All right. Remind me in about 10 minutes to call roll again. Okay. Some of the things we were talking about earlier today are mentioned here. Things like, when they talked about moonstruck, what do they mean by that? Lunatic, are those related? I don't know. We won't go to that. Moonshine, those from Appalachian might know something of that. Okay. Moonlit setting, so lots of things about moon. The other languages that use these, moon is related to words that mean to measure, because we use that to measure time, as in months. Okay? Not going to read all this, but just a little bit of it here and there. Pretty interesting about Babylonians, Israel, Greece, Rome, all use lunar calendars. The Muslim world, literal obedience to the words to live by the cycles of the moon. Okay? And if you have followed anything to do with Muslim, you know their holy month is Ramadan, and it is always the same one because they do it so many lunar cycles. Okay? And of course, we don't live on a full lunar cycle. Okay. Here's what part of your lab will be. It's the first part of the lab, but you won't be able to do it now. You'll do it later. Okay. You're going to use about 6 observations of the moon over a 2-week interval. So that's, on the average out, shoot for observing the moon every other day. Now, you know that some days will be cloudy or rainy or something like that, or you might not be able to do it. But shoot for the best you can to make at least 6 observations. Try to make them every other day. If you miss one day, do it the next. Don't wait for the next every other day. Do it the very next day. Over something around the 2-week interval. Now, why a 2-week interval? For any given time, say at night, you may only have the moon visible for about a 2-week interval because it either would have not risen yet or already set for a given time. So that's what you're gunning for. Okay? Now we're going to talk about these observations first, then we're going to do the bulk of the rest of the lab. Okay? So part A is the observations. Complete lunar cycle. Lunar phases require 29.5 days. We mentioned that before. Okay? You will follow the moon for at least half of the cycle, so your observations will spread over the course of about 2 weeks. Okay? During that time, you'll be recording 2 types of measurements. Oh, and here comes Lauren. Okay? And she managed to get in just in the first half. Not quite, a little over half. So she timed it well, I guess. Right. Oh, here's a lab. just getting started talking about it. We haven't actually done anything on it yet. That comes really soon. Okay. So, you'll be making two types of observations regarding the moon. Okay? Actually, three in my mind. Okay? The first of these, you'll be recording every other day or as soon after every other day as you can, the phase of the moon. So I would say draw a little picture. Is it a full moon? Is it a half moon? Is it a crescent moon? Is it a gibbous moon? We're going to talk about that later. How big? Make your best estimate. You'll probably have several crescents, several gibbous, in there that shows whether the moon's getting bigger or smaller, and whether it's full, half, whatever. Okay? So that's one observation you're going to make of the moon. What is its phase at that time, those days that you're out looking at it? The second of those, the relative position of the moon relative to some local landmark. Okay? Now I'm going to talk about your choice to begin with in just a minute. But what we're talking about here, you're going to go to about the same place every night, whatever time. If you're a morning person and 5:30 works for you, fine. Okay? If you're a night owl and 10 o'clock works for you, fine. If you're really a night owl and midnight or 1 o'clock works, fine. Okay? You choose your time. Keep with the time. You also choose your location and state and always go to the same spot. So let's say I choose, this is really hard to do here, but if I were to choose this spot here, and I would say that little bit of the Ethel Hall building that I'm going to use, goodness, I can't see anything of it. I know there's a billboard. Over here is Bessemer High School. Over here, pick out things on your horizon and try to get something at least every 90 degrees or so, probably a bit more frequent than that. But go to your position, pick out those things. So what you're going to do when you can find the moon, say, well, it's pretty close to this one here and so high. We'll talk about how to do those measurements. But you do it relative to your local landscape. Other thing you're going to do is relative to the stars. That might be a little tougher, and we'll talk about how to do that as well. So let's first talk about choosing. So you're going to do shape of the moon, in other words, phase of the moon, where it is relative to your landscape, and where it is relative to the stars. Those are the three. So the first thing to do is choose your location. Okay? I'll just give you one simple one. That one guy did. I was teaching this class several years ago, and this guy happened to be a work study student for the evening coordinator. So he was here every night at 10 o'clock. Okay? He worked the front desk out there. So every night, I don't know if he chose 10, 15, whatever, but he chose some time when he was at work, and he'd go out into the parking lot. You where he was standing in the parking lot. He had Bessemer High School. He had all these landmarks there, and then he did all his tracking from that spot. That was real easy for him because he was here every night. Now he wasn't here Saturdays and Sundays, so he probably always shot for a Friday if he could, and certainly the next Monday. But he did. I think he lived close enough. He could have come and gotten in that same parking lot out there and done it even on a Saturday or Sunday. Okay. So, that was his choice, okay? What I would suggest, and here's what they say, you'll need to find a spot with relatively unobstructed view of the horizon and sky. This would be a terrible spot, okay? I can't see a horizon. I can see the treetops over there and stuff like that. I can't see much. That was a pretty good one because we could see most of this horizon. Where would be good places? Big parking lot. I don't know if it's safe or not. Weston Hills parking lot down there there's nothing there, okay? And no cars in the way and stuff. If you feel comfortable and safe there, or bring a bodyguard or something, that might be a very safe one. Maybe a local high school, the football field, you know, or baseball fields.
What about the track at Lawson?
The what?
The track at Lawson.
What is Lawson?
The track.
The track in Lawson on the Birmingham?
Yeah.
Okay, can you get there at night?
Yeah.
And you're saying, yeah, that would be fantastic. Okay? Something like that. Okay? Parking lot, ball field, something like that with a relatively unobstructed view. You need a few things on the horizon, like the goalposts or the light, the light fixture there or something. Yeah, you need a few things so you can mark it. Okay? So, the middle of a large open space with a few low-profile landmarks near the horizon is ideal. And you need to be able to get to the same spot every night, very close to the same spot, so those landmarks at the same position every night. So you're not moving to different things. Now, here's the problem. Not near bright sources of light. How well lit is the yeah, I don't know either. You really want a little light so you feel safe, but you don't want it very bright light, unless you bring someone with you or something like that. Maybe you can talk someone into doing that. Okay? So, you don't want a lot of bright light. I don't know how his back part of the parking lot was here. He seemed to get pretty good results, so you might be able to. If you can get out in the country somewhere, if you're from somewhere out in the country, you can go out in the country, big open field or something like that. That would probably be really good. Not many of us have that opportunity. Okay. It is important that you use precisely the same location for all your observations. So 6 or 7 observations you do every other night for about 2 weeks or so. Okay? So somehow if you can mark where you're going to be in that thing, that might not be a bad idea. Okay? So, timing your observations. You pick a time that you think you can reasonably be able to get there at the same time every other night for the next 2 weeks. If you live close enough to the ball field or the thing on the Birmingham campus, and it's easy for you, and you know you're going to be free at that time, do it. That sounds great. Okay? If I were doing it from my home, I try to put my dog out every night shortly after 10 o'clock. And for those 2 weeks, or those 6 or 7 times I do it, I try to make it right at 10 or 10:15 or something, so I'd be at the same time every night, and I make my observations there if I wasn't having to watch her. Okay, so she's a pretty good time to do that. Okay? Now, it says I'm going to give you instructions for when to start. That's really up to you. Here's the main thing you need. When you go out, you need to be able to see the moon. I mean, half the time the moon's on the other side of the globe and you're not going to see it. So only half the time. Now, lately, there's been basically no moonlight until sometime late in the night. So they have been good times for 10 o'clock. But it seemed like last night I could see a few more shadows. I didn't see the moon, but I could see a few more. So I bet you if 10 o'clock or 10:15 or 9:45 is the time you're thinking of, this is a good time to start. If it's 5 in the morning or something like that, you'll have to figure that out. You have a lot of night opportunities on you, okay? Because you work nights. But you decide. It is critical. It says it is important to use precisely the same location. It is critical that you make all your observations in the same time of night within 15 minutes. That's why I said 10 o'clock, 10:15, and 30. Maybe if I were doing it, I'd shoot for 10:15 so I could be on either side. Yeah.
How long do you want to keep this paper in
Say this again.
How long do you want to keep this in
You'll need at least 2 weeks. If you start tonight, 2 weeks. If you can't start tonight because the moon's not up yet, at the time you're going out there, then you have to wait till it's up and then start your observations.
Just saying, my location is going to have to be 2 different locations. I work on weekends, 16-hour shift overnight, and on Monday to Friday, my job is 45 minutes away.
Okay.
I would not be going back to my job.
Okay, well then you might try to do the one that you can do 5 nights. Try always do a Monday, Wednesday, Friday, and then skip, always have clear Monday, Wednesday, Friday night to do the best you can. Okay? And if you need to go over 2 weeks and you can still see the moon, that'll be fine. Okay? All right, good question. Okay? Now, it says the first observation may require as much as half an hour. So go out early the first time. Okay? And make your observations. And after that, it says about 5 minutes. So within, if you pick your middle time, like I was going to do 10:15, then the first night I go out at 10, figure I might be there as late as 10:30. Okay? I don't think I would be, but I might. Then after that, do within 5 or 10 minutes of 10:15 every night. Okay. Recording your observation. Now they give several suggestions here. They talk about drawing paper and I've had several people do various things. Most of the time, I don't need what you draw. I just need the results of it. Some people have turned it in, and some have turned in poster board. I don't need it, but they have. I welcome it. Shows you really got into it. You can just make your observations down on a pad or a piece of paper to keep up with the paper. So record your observations of it. Okay? Now, they give some ideas here about the width of your outstretched hand is about 22 degrees. So you can talk about how far the moon is above the horizon, say. There's your horizon. There's 22, 44. You can do like that. That's sort of a pain in the neck in my mind. You know, they give others here. The width of your fist is about 8 degrees, so there's 22 and 8. Okay, that would be 30. If you want to do that, you certainly can. Okay, the width of your middle fingers, 3 now. Okay, yeah. Never mind. I'll give you 1. Okay, 3 middle fingers. That would be about 5 degrees. The width of your index finger at arm's length is about 2 degrees. That's a tough way to do it. To me, a little easier, get you a yardstick or a meter stick and go out there and hold it at arm's length on the horizon and say how far up it is. You'll probably get that. And that's what you can use. How far up, how many meters, always have the 0% place, or how many inches, up. That to me would be the easier way. And then you can do it for, hold it this way for, say, if you're using that tree over there, and then you're this far and then up, how many inches this way, how many inches that way. That would be a good way to measure. So get your directions, write it out, up, down, be sure you go through that. And they say alternately you can carry a ruler with you, measure, and always have it at arm's length. Okay. Now, so, first thing, shape of the moon, phase of the moon, that kind of stuff. Record that every other night. Be sure you have that on your pad. You can draw little pictures. I've had people have, it shows a 4.5 moon to less than a full moon. The next night, a little bit less or more, whichever happens to be. Now, the next thing you look for, so the position of the moon relative, like I said, if that's a tall tree there, you know where it's going to be every night, or the goalpost or light post, whatever, okay? And then the moon is so many inches this way, so much that way, okay? That is a good position relative to landmarks, okay? If the moon moves over here, and that's hard to measure from that one, pick another one over here and do it. That's why it's good to have those landmarks plotted out, maybe marked on your thing of where they are. So you get an idea of what the relative motion of the moon is. Now here's the other one. Now this one may be tough, especially in the city. And you need a nice, clear, fairly night to see this. So that first time you go out there and see the moon well, pick out some pattern of stars near the moon. Something you'll be able to see. Oh, that looks like a W to me. That looks like a diamond to me. That looks like a big triangle. Pick out some pattern you'll be able to pick out every night at that time. It's going to be at about the same location, right? So pick that out and then do the same thing. How close is the moon to that? So it's 3 inches to the left of it, or and so many inches above it, or something like that, or below it. So again, use your ruler or whatever method you use to locate the moon relative to that easily identifiable pattern of stars. So pick that out, maybe draw a picture so you know exactly what to look for. So here are the 3 questions you answer at the end of this. How would you describe the night-to-night path of the moon with respect to the landmarks, the trees, the posts, the light, or whatever you're using as your landmark? How would you describe it? And if you know your directions, the other thing you can carry with you is a compass if you wanted to. And if you're standing in the same spot and you get the compass in, or a lot of your phones will have compasses, don't they? Okay? Take it with you and look at it. Now, don't get it really groggy, but look at it and say, that tree, over here, it's the moon is here, and the next night is here. It seems like it's going east to west, west to east, northeast, west, southwest. However, it seems like it's going night to night. That's the answer first. How would you describe the night-to-night path of the moon with respect to the landmarks around your observing site? That big tree at 45 degrees from true north there, it's going higher in the sky and going east to west, or something like that. So that's going to answer the first question. Second, in which direction does the moon move with respect to the stars up there, that pattern of stars? Is it going north, south, east, west, right, left, up, down, whatever it's doing relative to that group of stars? That's going to be your second question. So that's why you make the observations every night for about 2 weeks. Every other night for about 2 weeks. And then the third one, the graph. Okay? Now, day 1, okay, or day 0, that's your first day you go out there. What is the fractional illumination of the moon? Okay? Is it about a quarter illuminated? Is it half illuminated, 3/4, 1, or something in between those? Okay? Half, you'll see almost, this would be half. If that's what you saw, that's a half. Okay? If it was all light, that would be 1. 3/4 would be that part. Okay? 1/4 would be this part. Okay? So you estimate what fraction of the moon. Day 0, 2 days later, or 3, whatever the next day you do it, what is it? It's either getting more or less, so it's either going up or down on the graph, and then it may peak and then come down. It may do whatever. So that's the third thing. For those, and you can do it up to 20 days, it says. So if you need to go more than 2 weeks, you certainly can, because of work or weather or anything else. All right. That's your homework, okay? It's going to take you at least 2 weeks to do, and get started as soon as you can see the moon, at the time that you can be there, at the place you can be. The rest of this we're going to do, part B, we're going to do together as a group. Lunar phase nomenclature. We've already talked about this. The new moon. When would you typically see a new moon? Second? Not necessarily. Okay, it may be this month, it is, but not necessarily, because you know that it's on a 29 days thing. Months are not 29 days. Okay, so but a new moon, you're generally not going to see a new moon because you're looking at the dark side, right? And if you do see it, it's usually going to be during the daytime. If you look up there in the day sometime and you see, that's the moon, isn't it? But you don't see any bit of it lit, that's a new moon. So you're going to miss a new moon at your observations earlier. So that's the new moon. Okay? Now, a crescent moon, that's just when a little bit of the moon, now this is right here, a little bit of the moon is lighted, just a little bit. And that's usually going to be, again, you'll see those almost more in daylight hours than you will at night hours. At night hours, it's going to set real soon or not be up very long. Okay? The half moon is one that looks just like that. any one of those looks like a half moon. Okay? If it was a new moon and moved toward the crescent started getting bigger, that's called the first quarter, when it's moving this way. Okay? The last quarter is when it's gone from full and is getting less every day. That's the last quarter. Okay? Now, a crescent moon is when just a little bit is lit. A gibbous moon is when most of it's lit, but not all. Okay? More than half. Crescent moon, less than half. Okay? Now, the moon's going from here to here. New moon that you don't see any lit. The first quarter that you see the first half moon there, and it's getting crescent in between, but it's growing every night. We say that moon is waxing. In other words, the lighted part is getting bigger. When it's over here, and it's been a half moon, but now it's going to be less than a half, so the crescent is getting smaller. That's called a waning moon. So it's waxing here, waning there. Okay? These are just terminologies. Okay. Now on page 383, that's where we're going to do the bulk of the lab. And it starts at the middle of the page, not at the top of the page. The figure 49.1, okay, is a picture that looks a lot like this, doesn't it? That's why I have this up. Can y'all see this well enough, or do you need Taylor to turn off this light? Huh? Okay, not that one. Okay, good. Okay, now here's two differences between what's on your graph, on your sheet, and this. And I highly recommend you use pencil, okay? Because if you make an error with ink, it's going to be really hard to undo. So if you got a pencil, use it for this part. Okay, here's the two big differences. In this one, the sunlight is coming from this way. On your graph, the sunlight is coming from that way on your sheet. You see? So don't make yours look like this. Okay? Second difference, this shows 4 moons around the Earth. Yours has 8 moons. You have one here, 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 and here. Okay? Now, the first part, this is not hard, but please be careful with it. Okay? Now you see they've already done the Earth for you. The Earth is here in the center. What you do for the first part here is draw a vertical line through each of those moons. A vertical line just like they have here. A vertical line top to bottom for each of those moons. The side toward the sunlight you're going to leave white. The side away from the sunlight you're going to color in. It's exactly the opposite of these, because these, the sun's coming from here. On your lab, it's coming from there. So you do it exactly opposite. Vertical line, this side's white, you color in with your pencil, preferably, the back half of the moon on all 8 of those moons. They look exactly the same, just like these look exactly the same. Okay? Only it's reversed. Your side will be dark over here. That's what you color in. Leave that side white. Does that make sense? For all 8 of those moons, draw a vertical line and color in the left half of that moon with your pencil. Just like the Earth is done there. Okay? Just like the Earth is done there. Not too hard. Vertical line, the back half dark. If you have any questions, please ask. Don't make some backward mistake. Okay? Any questions? If anyone needs a pencil, I have a couple up here. Do you? Okay. I don't know how good that eraser is. Good catch. Okay. Anyone else need a pencil? Okay. When you got all 8 colored in, halved and colored in, let me know. Please do it the way, just like the Earth is, they're only smaller. The Earth here on this didn't ask, was anyone likely to see Cassidy? You have her in any other class, or anyone know her? Don't say you can give her a lab. Okay. Everybody got it done? No, so someone's still working. For the purpose of this lab, ignore this one because here the sunlight's going to be coming from well, yeah. Ignore. Well, I'm going to use dark for that. Ignore the sun over here. Ignore these. Okay. What I'm going to do is draw this with the sunlight coming from this direction, just like on your lab. Okay. And I'm not going to do all of them, but I'm going to. I probably should do the moon in dark outline because you probably able to see this. I'll do these. Okay. What's that? Right. You mean? Yeah. 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 Okay. You're right. You can do that, and it looks just like that then. So you can do it just like these if you want to. Clever thinking. Okay, so you can do that. So maybe I won't do this anymore then. Okay, you get the idea. Everybody got it done now? All right. Now, what we're going to do with your picture, and this is why I was going to do this, we're going down to the bottom of the page. So you're on the Earth. You're looking at the moon. Okay? I can't turn my computer upside down. It wouldn't work. I don't think. I'm not going to try it. Okay. Okay. Okay.
Can you draw it on the whiteboard for us?
What's that?
Can you just draw it on the whiteboard?
On the whiteboard? This isn't helpful this way? Okay. You might need to do twice the work then. Okay. All right. Well, then what I'll do is go and get out of this. Needed to get out of it anyway. Okay. All right. Which color am I now? Okay, I'm going to get back to dark. Okay. All right. Well. Yuck. Okay. Here's the sunlight over here. I don't know if you can see it. Sunlight's coming in from this side. Okay. Let me draw my little moons here. Obviously, these aren't perfect, as most of my stuff is not perfect. Okay, you've drawn your vertical lines. With the sunlight to the right, the back half is dark. So you've done that for every one of them. And this, by the way, is 1, 2, 3, 4, 5, 6, 7, and 8. Okay, you've drawn these in. I'm not going to do them all, but just give you the idea. Yours will be better, much better looking than mine. Okay? Now, you're on the Earth here. There's the Earth. When you look at number 1, what do you see?
Waxing.
Second?
Waxing.
Okay, first, what do you see? What does the moon look like when you're here looking at one? It's dark side of the moon, exactly. So number 1 here, take your little marker. I'm sorry, I don't have room at the bottom. Number 1 down here is going to be totally black. Nothing is lit on the moon, is it? Yay or nay? Yeah, when you're looking here, all you see is the dark side of the moon. That's all you're looking at. And it's going to be in the daylight, okay? In the sun. So it's even harder to see. Okay? So that's what you do for number 1. So that's number 1 at the bottom. Is that making sense? Okay? Number 2 at the bottom. Okay? Now you're here on Earth and you look up and most of what you see is dark again, but you see just a little bit that's lighted. Okay? So I would do just a little bit of a curve here. Always the lighted side is toward the sun, toward the right, and color in most of it. You see? My circles are really lousy, but just a little bit of it is left white, all the rest of it is dark. That's number 2. Do you agree with that? That's what you see when you're looking at that. What do you see when you look at 3? You see exactly what number 3 is, don't you? So draw that one to look just like number 3. Okay? When you go to 4, what do you see? Most is light, so just the back little sliver is dark. So color that in. That's number 4. Okay? When you look at 5, what do you see? All light. So don't color in a thing on number 5. You see the completely light side of the moon, it'll look just like this Earth here is here, not the one on your thing. Leave 5 alone. Don't touch it. Don't try to color in anything on 5. That's your full moon. Okay? Number 6 looks like what? Say again? It basically looks just like 4 again, doesn't it? That's exactly right. Looks just like 4 again. So color in 6, so just like 4, that's how you have 4 look like. What does 7 look like?
Just like 3.
Just like 3 and just like 7 here. So color it just like that. Okay? And what does 8 look like? Second?
Like 2.
Not all dark. You see just a little bit of it like it looks like 2 again, doesn't it? Yay or nay? Yay. Okay, looks just like 2. Your 2 should look better than my 2. Okay? Now, has everybody got those? Did I do them too fast? Does anyone need me to go back and talk about any one of them? Okay? So 1 is totally dark. 2 and 8 look sort of like this. Just the edge toward the sunlight is light, and most of it's colored in dark. 3 and 7 look just like they do there. 4 is the opposite of 2, kind of. Your wedge is at the back, and it's dark. Most of it's light. 5 is just leave it alone. Don't do a thing to it. It's a full, all white. And 4 and 6 look just alike. 7 and 3 just alike. And 8 and 2 just alike. Any questions? All right. Now we finally go to the top of the page. In the spaces below, write down the names of the phases corresponding to what you just did at the bottom. See, the figures are down here and the verbiage is up there. Sorry, it's sort of backwards. Okay? So number 1, what do you call number 1? And what you put here is write down the names of the phases, okay? And the names of the phases you find on the previous page, and they are new moon, crescent, half moon, or first quarter moon, whichever you want to call it. Gibbous, full. One of those is going to be every one of them, except numbers 3 and 7 They can both be called half moons, but one, if you call one like 7 the first quarter moon, then 3 will be the last quarter moon. So it depends on what you want to put down there. So the first thing you put in each of those things is the phase of the moon. So you should have a phase of the moon in all 8 blanks. But save some room, because now for the new moon here, it's neither waxing nor waning. Because it's all black. And the same thing for a full moon. It's neither waxing nor waning. Okay? But on all the rest of them, 2, 3, 4, 6, 7, and 8, you need to put one of those 2 words, waxing or waning. So you put the name of the phase first, and all of them will have the name of the phase. 6 of the 8 will have either the word, 3 of them will have waxing, and 3 will have waning. Okay? So you want to call out, y'all want to work together on this? Okay. So you got what you need to do? Okay. Then knock yourself out. Not literally, but physically. Okay. If you, what's that? Okay, if you want me to do that. What would you say number 1 is? Is that what you mean? New moon. Is it waxing or waning? Neither. Don't put any face. All right, new moon, that's his face. What's number 2? Second, it is going to be waxing. But what? Yeah, waxing crescent or a crescent waxing, either one. Okay? Do you have a question? Okay. Y'all can work together, help each other out. What would you call 3? Huh? You can either call it a first quarter or someone else said half moon. Either one you want to call it. Is it waxing or waning? Huh?
Waxing.
It's waxing because it's bigger than it was the night before. The white part's bigger, and the next white part's going to be even bigger. So it's waxing. Number 4. What do you call that?
Waning.
It's waxing for sure. But what is it called? Gibbous. It's a gibbous waxing or waxing gibbous. I don't care which. Most of the time they say gibbous waxing. I don't know why. A gibbous moon waxing. Getting bigger every night. Number 5. Full moon. Waxing or waning? Neither, because it's full moon. Okay. All you're right for 5. Number 6 is waning for sure. Gibbous. It's a gibbous because most of it's lit, but it's getting less every night, so it's waning. Okay? Number 7. You can either call it a half moon or a last quarter, if you want to call it that. And what's it doing? Waning as well. And number 8. It's what? I can't hear you. One more time. No. Number 8 is just a little bit. It looks like 2. That's a crescent. And what's it doing? Waning. It's getting less every night because it's soon going to be a new moon. Okay? Now, just roughly, the full cycle is about 28 days, or 4 weeks. So half the cycle would be 2 weeks. The quarter cycle would be 1 week, and so those are about 3.5 days each one. Okay? Just to give you that idea. Okay. Now, when everybody's finished with page 383, if you're not, please ask the questions. If you are, then let me know, and we'll go on to the last page. I forgot to call roll, so while y'all are doing it, Ed's still here. Pius is still here. Cassidy didn't make it in yet today. Jessica's still here. Christy's still here. Chris is still here. Guy is still here. Kayla's still here. Adam's still here. Justin's still here. Jordan's still here. Lauren's amazingly still. No, I didn't say that. Andrew Corey's still here. Okay. Everybody finished by now? Still see one person writing. Okay, you got it. All right, let's turn to 384. Last page, all I'll said. All right, now let's think about this. Do y'all need this anymore? Okay, I'm going to turn this off. And shut this down. Okay. Now, if you want to turn on the light again, I don't think anyone. Okay. Don't want to. She likes it. No. Okay. All right. At what time of day would you expect a full moon to rise? Now, what you need to think of here is sun. Where's the moon on the earth? Where is the moon when it's full moon? Opposite me. Now, the rising and setting all depends on my spinning. So when would you expect the full moon to rise? Okay. Wouldn't it be about the time the sun is setting? Because it's exactly opposite. Okay, and since the sun sets at different times, let's just say 6 p.m. Does that make sense? In the summertime, sun doesn't set that early, but in wintertime, it sets much earlier than that. The moon would be about 6. Right? Does that make sense? p.m. Evening.
Can we just write when the sun is setting?
What's that?
Can we write when the sun is setting?
And yeah, you can put that if you want to. Okay. How about a new moon to rise? Where is the moon when it's the new moon? It's on the same side as the sun. And remember, it's rising and setting. It depends on my training, not anything to do with it. So when would it rise? When the sun came up, because it's in between us and the sun. So that would be about sunrise, or 6 a.m. Okay? Does that make sense? Okay. The first quarter moon to rise. Okay? The new moon rose with the sun. The full moon rose when the sun was setting. So the first quarter moon would be rising about what time? Say again? In between, what's actually in between 6 a.m. and 6 p.m.? Midday. Around noon. That's when your first quarter moon would rise. How about the third quarter moon? Say again? At midnight. Very good. Right around midnight. I would never see that, of course. Okay. How about the first quarter moon to set? First quarter moon to set. At midnight. 12 hours later, exactly. Okay, around midnight. And the new moon, or very thin crescent moon to set. About 6 p.m., right? Right at sunset, right? Oh my goodness. That was way too easy, wasn't it? And I'm cheating you out of bunches of your tuition dollars here. I feel terrible. Okay?
Yeah, I'm sure we'll all go home and have a good cry about it.
Yes.
Okay? Okay, good deal. All right. Now, question. Can't turn this in, of course, until you finish another part. Could begin tonight, but I don't know if the system is going to be up tonight, or whenever it is time of day you're going to be watching it. Watch from the first time you see it, okay? And then start for 2 weeks from there. Yes? Say again? They should.
That was changed to February.
So,
on the call that we got to do observe.
the observing parts? Is that what you meant? I thought you were pointing at that. Okay. I thought we just were in here. They should be, I would say, somewhat similar. Okay, but you'll get the most benefit if you do it yourself. But if you want to work in a group, that's perfectly fine.
What type of the cloud?
What's that?
What like for the cloud?
The cloud.
Okay, what about it?
What for the cloud?
Okay. The problem with clouds is you would be able to pick out the moon if you wait a few minutes, unless it's totally overcast. The trouble is you won't be able to see those stars. That would be the worst part. So, but if it's that cloudy at night, try it the next night. Don't wait 2 nights. Do it the next night. Try to get it as soon as you can, as early as you can. And a 2 to 3 weekend. Oh, okay. Give me a water trash, okay? Okay, thank you. I will take it, I'm not proud. All right. I'm going to shut down Screencast-O-Matic. Y'all have a good weekend here. Moon watching.